Okay, so what we have done yesterday, resume of our lecture of yesterday, okay? I will tell you, when I was a student, I had a very good professor in geometry and linear algebra. His name was Francesco. He wrote a very good book, and he was old, very old, more or less my age now. And he was giving a lecture in this way. The first third was the resume of the previous lecture. The second third was the new subject, and the last third was a preview of the next lecture. So he was repeating 3 times the same thing. Okay? And I think this is a very good way for proceeding. Okay? Of course, I will not do exactly the same percentage. We try to go a little bit quicker. Why? Because I hope that you can peruse the video recorded lecture. I started video recording my lectures before MIT decided to do the same. Okay? And I think it is very good because you can stop, go back, hear another time. I think that with this technology, teaching and learning is changing dramatically. Okay? Good. A colleague of mine, please. A colleague of mine is pulling my leg, and he said that I am a little bit strange because I start writing from the center of the blackboard. Probably somebody has seen some of my video recorded lectures, so now I try to start writing from the left. Okay? So, what we have done, we have introduced Q1, Qn, denoted with this symbol. These are the Lagrange coordinates These specify the kinematics. Okay, so as I told you yesterday, I repeat now another time. This is a typical mathematical theory. We are not studying physical objects. We are studying other theories. This is a theory which is teaching us how to build theories. Okay, learn this. Physicists are describing phenomena. Mathematicians are describing theories. A mathematician is developing theories whose subject is how to build theories. While a physicist is describing physical phenomena with his theories. Of course, this is a rather sharp and not true statement. You will find many physicists who claim that they are as good as mathematicians. Okay, but this is another story. Okay? And probably they are true, they are right. I mean, it is a rather sharp statement. So now I tell you the following. You want to describe a phenomenon. Which phenomenon? I don't know. I don't know. I do not want to know. It is a phenomenon whatsoever. What I have to do at the very beginning? Specify its space of configurations. So I must find a set of coordinates which describe every state of the system which this model is describing. You cannot start your theoretical analysis without specifying the kinematics. This is the beginning. Okay. Next step, you must specify motions. I want to make clear, as I told you yesterday, I was teaching for many years to engineers, and they did not know mathematics, but they believed to know some physics. I was also teaching to physicists. Physicists believe to know everything, and this is not always true. Okay. Now I was surprised, please stop me all the time, that somebody did not accept easily my statement about friction or dissipative phenomena. So tell me always. So now I'm telling you, I'm sure that you have seen a ball which falls down, receives an impulse, and jumps back. Okay? This kind of motion, which is called impulsive motion, by the way, impulsive motion is the, I don't know if I can say this in English, but I will tell the same, is the horse of battle. Do you know what it means in Italian? Horse of battle. It is the speciality of Italian school. Levi Civita, I hope you heard the name, wrote some papers about impulsive mechanics. Why this is a strange phenomenon for mathematicians? Because the velocity here in the point of impact suffers a dramatic change. Of course, modeling is a difficult subject. If your ball is modeled with a material particle, this material particle arrives at the pavement, at the obstacle, and then suddenly suffers suffers a jump of velocity, and after impact it has a very different velocity. So the plot of velocity is discontinuous. Okay, this is a paradox, because as Newton said, natura non facit saltus, which means nature is not jumping. Okay, why this is happening? Because this ball is not a point. The true nature of a ball requires the need of describing its volume, which is not vanishing. So instead of using this model, material particle, if you really want to study the impact, you need to consider the ball with an extension. You must assume it is deformable. You must study the fact that the ball arrives here, then in a subsequent instant it is doing something like that, then the deformation energy comes back, the ball is doing like that, and then it is moving like that. So what it means? The model material particle is not detailed enough to describe impacts. If you force your modeling technique to use the material particle scheme, then motions must be discontinuous in velocity. And this implies some mathematical difficulties. When you have something which goes to infinity, okay, if you have a velocity like that, okay, you have that here the derivative goes to infinity. Okay, when you have a mathematical function which shows singularities, you are wrong in the mathematical modeling. Mathematics refuses to do what you ask it, and it revenges, showing you some strange phenomena. So this is usually a signal that you must change your mathematical model and develop it in a better way, a more detailed one. Okay? So singularities are very interesting for the mathematician and the physicist, because in every singularity there is hidden a model which has to be refined in general. Okay, so I wanted to tell you this example. By the way, this example has been studied by Newton. It is a paradigmatic example of this kind of singularities. So when you fix the class of admissible motions, you are limiting your model, the range of applicability of your model. Okay? Okay. Now, final step, I must specify the motions which are really experienced by your system. You want to predict the motion of your system. So you introduce a Lagrangian. This Lagrangian is a function of Q and Q dot. Okay? And you built the action functional, like integral between T0, Tf of L of Qt, Q dot T, dt. Okay, you don't have problems with composition of functions, I hope. Okay, this is a functional. Be careful, sometimes following the Italian mathematical tradition, I write this symbol for meaning that A is a functional of Q. You know, if I write A of Q, it means that I have a function in Rn. This is not a function in Rn. The domain of this functional is the set of motions. So for remembering that the element in my domain is a function, I place the brackets with the dot inside. It is a convention I hope you can accept. Okay? Okay. Now, I must tell you that many physicists, but especially many engineers, refuse this meta theory because they claim that nobody knows how to postulate a Lagrangian for a given mechanical system. Okay. Now the question is that, and we will talk about this tomorrow, okay? The problem is that every theory needs conjectures. This is very well known since the philosophy of Aristotle. A theory is a creation of our mind. You wake up one morning and you decide, I want to conjecture that this theory works. There is no way for understanding a priori if a given theory works or not. You must develop it and see if it is predictive or not. So what we are telling you is that the creative moment of in the process of inventing a theory consists exactly in the choice of a Lagrangian. Okay? How can we prove that a Lagrangian is good? Developing the theory. Checking if this theory is producing the right predictions. And if your chosen Lagrangian allows you to predict what happens in reality, then you can say that your theory was good. For instance, I introduce the Lagrangian of the solar system, I make all calculations, I predict the motion of the planets, I place my telescope in the sky, and I find the planet where I predicted. Then I can conclude that my Lagrangian was good. This is the essence of so-called Galilean experimental science. Okay, but tomorrow we'll spend more hours on this subject. Once you have postulated a Lagrangian, you impose that the first variation of the action is equal to 0 for every delta q, and you impose isochronous variations, okay? And after we discuss this in whole detail, this is a condition for being minimum for the motion. Okay, I want that the motion minimizes action. Okay? And with a trick based on integration by parts and Taylor expansion, which I showed you in detail, what we get? We get dl over dq minus d over dt dl over dq dot has to be equal to 0. This is a necessary condition. If the motion minimizes action, then it must verify this equation. Okay? Now we will talk about this equation from a mathematical point of view. And I hope that you have learned enough about ordinary differential equations. Otherwise, you tell me and I will try to give you more details. Okay? Ordinary differential equation is a subject of mathematicians. Okay? So you should know something about this. Remark that this equality you could write changing the sign in this way, because 0 and minus 0 is the same thing. My definition of a good mechanician is that he writes this equation in this way. Why? Because you must remember that you got it integrating by parts. Okay? So, if you write it in this way, it means that you remember how you got it. Okay? Okay, now, you have that qt0 is equal to q0 and qtf is equal to qf. So, among the motions which have q0 value at the instant t0 and qf value at the instant tf, those motions which minimize action must verify this differential equation. Okay? Now, when Lagrange started studying this problem, he understood that there is a problem. Usually, when you study a given system, you don't know its future positions. You know only its actual position and possibly its velocity, its initial position. So, usually one knows Q of T0 and Q dot in T0 so one shoots a picture of the system in a given instant and he wants to predict its evolution in the future. So what we have usually is what is called an initial condition problem for ordinary differential equations. Philosophically speaking, this is a rather delicate issue. One observes a motion, he knows the initial condition, then the final condition, and he says, okay, nature has chosen to minimize action in this motion. Okay? And to minimize action, it has to verify this ordinary differential equation. Okay? Agree? Now, the question is, I want to predict future, so I want, knowing the initial state of my system, to say what will be its time evolution. So the idea is, following Lagrange, I give initial position and velocity, and I impose the validity of the ordinary differential equation, which I should not say ordinary for the moment, of the differential equation which I obtained after integration by parts imposing minimization of energy. So mathematically speaking, following Goursat and Cauchy, I have to solve now, in general, the following problem. I have a function f of q dot, q double dot equals 0, because okay, please follow this reasoning, because you are mathematicians, you should not be frightened by this. I have L, which is a function of Q and Q dot. Okay? I calculate the partial derivative of L with respect to Q dot. Okay? What I get is a function of Q and Q dot. Always, not always. If L is a linear function of Q dot, I calculate the derivative and I get a function of Q only. Okay? So, we start suspecting that if inertia laws are valid, I know I have some difficulties. I hope that you have studied standard Newton equation, force is equal mass times acceleration. After Aristotle, Greeks understood that the force is not causing velocity, but it is causing acceleration. So we know that in general this equation of motion must have accelerations in it. So second derivatives with respect to time. Okay? So if by chance this partial derivative does not depend on q dot, you calculate the time derivative and you have a velocity. You don't have an acceleration. So this Lagrangian must not be linear in q dot. The derivative, partial derivative with respect to q dot must depend on velocities. Cannot be independent of velocities. Okay? So you calculate this derivative, you get q double dot. dl over dq depends on q and q dot. So in general you have this structure. This is a differential equation whose unknown is the motion q of t. Okay. So an initial problem for this equation is this one. So the problem is to find a function q of t such that these initial conditions are verified, and for every instant t this equation is verified. I'm talking like a mathematician now. Okay? So this is a standard existence, possibly uniqueness problem to be solved.
So that equation is verified only if that is non-linear, right?
No. If this equation, if L is linear, here you don't have q double dot. Okay? If this partial derivative depends on q dot, then when you calculate this time derivative, you get q double dot. Okay, I think it is needed that we stop a moment and we make an example. Okay, so you understand what I'm talking about. But before going ahead, let me tell you this. Forecasting the future means to know the velocity and position in a given instant, and to be able to say the configuration of the system in all future time instants. You agree? Forecasting the future, we are not using astrology for this. We are not using reading the bottom of the coffee, Turkish coffee. What we are doing? We are using ordinary differential equations. Modern science is based on our capacity of solving ordinary differential equations. Okay? And what is terrible is that some years ago, a revolt of my students in engineering sciences was against this craziness. I wanted to impose them. I wanted to teach them ordinary differential equations. They told me that in modern engineering, ordinary differential equations are useless. Okay? Everything in our predicting models is based on a solution of an ordinary differential equation. I am very worried. Middle age could be very close now. Because when you start telling that science is useless, what you will have is another middle age. Okay? But we'll come back to this. Let's go to the problem. So, being able to predict future means being able to solve this ordinary differential equation. Why we call it ordinary differential equation? Because the unknown is a function of only one variable, so you don't have partial derivatives in your equation. Okay? Very well. Now, before proceeding, I think it is suitable that we start with an example. So, I postulate this L of Q and Q dot. Let us start with Q equal Q1, only one variable. Okay? And as a Lagrangian, I use 1/2 K Q minus Q0 square, Q bar square, okay. Then I have minus 1/2 M Q dot square. Okay? I'm sure that you have already seen this.
The second part is kinetic energy, yes, but first part is what kind of potential?
It's a potential, elastic potential energy. But look, I don't want to give names to these things. If you will be patient and if we manage to find some extra time for giving you more examples, I will show you that this could be the Lagrangian of an economical system. Okay, so in the mechanics of a material particle, this is kinetic energy with the minus sign, and this is a potential energy of a spring. But this could be also the adaptive cost of a production system. So for the moment, this is a Lagrangian. Okay. Now, to write the Lagrange equation, I need to calculate dl over dq, and this is equal to kq minus q bar. I hope, you know, I need to stop because I didn't stop. So I tell you a terrible thing which happened to me. A student, a young girl, engineering student, she said that the derivative of this function is this function, okay, so the derivative of a linear function is the constant. Okay, so she generalized this rule and she decided that the derivative of this function is this function. The rule is easy. Why you are wasting time calculating the limit of the incremental ratio for calculating derivatives? The rule is simple. you take one x away, and that's it. So the derivative of this function for this clever girl was this function. Why wasting time with calculus? Okay? This is the beginning of Middle Age. Okay? And she said that I have a twisted taste for complicated things. She knew how to calculate the derivative. What is terrible is that this girl is now an engineer working for the Italian state. So you understand why bridges are falling down. Okay, let's go back to our calculation. dl over dq dot is equal to minus mq dot. Okay? So consider that these partial derivatives are made on L without considering motion for the moment. Okay? Then what I have to do, I have to write kq minus q bar. Yes?
What is q bar?
Sorry?
Q bar.
Is a constant.
Function, constant function.
A number is a constant. Okay. Or, yes, it is a constant. We will interpret it immediately. Okay? Then, be careful with the sign. You have minus d over dt of dl over dq dot, which is minus m q dot equal 0. Okay? So, you get that this is plus, okay? So at the end you get R. If m is a constant, this is not a rocket. When you have a rocket going towards the sky, its mass is varying. Okay? So the equation of a rocket is a rather difficult subject. Okay? We assume that m is constant. Okay? So what we get is mq double dot. So I am answering to my Buddhist friend. If here you have a quadratic dependence on q dot, you calculate this derivative, you have a dependence on q. When you calculate this derivative, you get the second derivative. Okay? And this is equal to minus q bar. This is the famous equation of harmonic motion, which I hope you have studied sometime in your life. Okay? This is an example. Please don't go around telling that I'm crazy and spending a lot of efforts for giving you the equation of harmonic motion. I gave you the theory of every discrete model. Give me a Lagrangian whatsoever, these are the ordinary differential equations governing it. Okay? I gave you an example. Why? Because very politely, sorry, I will change, I will put the leg of another student next time. I will start with him. Okay. Our Buddhist friend wanted to know how it is possible that in this equation I wrote before, in this equation, there is no q double dot. It could be. If the Lagrangian depends on linearly on q dot, this partial derivative depends only on q. You calculate the time derivative, it depends on q dot, And this is a first order differential equation. Okay? If instead the Lagrangian depends on Q dot in a non-linear way, then in this equation you have a second derivative. So we can include in Lagrangian mechanics Aristotelian physics. Aristotle said something in words like this: forces are proportional to velocities. All Aristotelian physics was based on this assumption. Instead, Archimedes, Galileo claim that the force is producing accelerations. In the Lagrange framework, these two possibilities are both included. Look, it is a beautiful theory of theories. It even includes Aristotelian mechanics, if you really want. Okay? Okay. We will give you more examples, and I will ask you to make some exercises, because you must start practicing Lagrangians. Okay? Okay. So now, let us look at this system f of q dot, q double dot equals 0. What we want to prove? We want to prove a theorem of existence and uniqueness. This is what mathematically translates the philosophical approach, which is called mechanical determinism. Epicurean philosophers, and I claim to be an Epicurean philosopher, state that the knowledge of the present allows us to predict the future. Okay? Mathematically speaking, mechanical determinism is translated in this theorem. Given the initial state q t0 equal q0, q dot t0 equal q dot 0, there is a unique solution of this ordinary differential equation. Okay? So, if you believe that the present uniquely determines the future, your Lagrangian must be such that f uniquely determines the motion once you know the initial conditions. Do you know when this formulation of the problem has been established? In Paris. Where? In Paris. When? During the French Revolution. Here there are some non-European students. You forgive me if I will very proudly tell you that Europe produced French Revolution. A revolution in which noblesse was kicked out of power, and in which mathematicians were allowed to design societies. If you go to Paris, in the Eiffel Tower, around the crown of the second floor, you have all the names of big mathematicians who changed the human history. Okay? You find something like that also in Moscow University. Okay? Also Soviet people liked this idea. Okay. mathematicians must transform into a theorem and into an algorithm the philosophical demand of mechanical determinism. Okay. Now, for a general function of this structure, this existence and uniqueness theorem cannot be proven. Peano, another Italian mathematician, has proven that there are f's for which the solution is not unique. Okay? It is the famous Peano phenomenon. So we limit a little bit the structure of this function. We assume that we can write something like that. Q double dot equal L of Q and Q dot. If your ordinary differential equation has this form, we say that it is in a normal form. Now, my dear friends, this is not so difficult to understand. I mean, the reason for which a function, an ordinary differential equation, for having mechanical determinism has to be like that. Why? Because you have initial conditions. You place it inside here, you know acceleration. Okay? If you place here L of Q0, Q dot 0, the initial conditions, what you get, Q double dot 0, the initial acceleration. Then, what I'm telling you is not a theorem, it is an heuristic reasoning, which we will need to make rigorous later. Okay. If I know Q double dot 0, I can tell that Q dot at the instant t is equal Q dot at the instant t0, which I know, plus Q double dot 0 times t minus t0 plus infinitesimals of higher order of t minus t0. Taylor expansion. This other useless subject of which engineering sciences can avoid the use. Okay? So we leave them without Taylor expansion if they like. Okay? So if t is close to t0, you get Q dot of t plus delta t with this formula. Okay? Similarly, Q of t is equal to Q0 plus Q dot 0 t plus Q double dot 0 t minus t0 plus t minus t0 squared over 2 plus infinitesimal of higher order. You know this, you know that, you know that. You can estimate Q at t plus delta t. Then you continue iteration, and delta t after delta t, you can build the whole solution. I am delineating the algorithm which is used for solving ordinary differential equations in the normal form. This is not a theorem, this is a finite difference scheme for solving ordinary differential equations in the normal form. Okay? So it is clear. Do you want determinism? The ordinary differential equation has to be in the normal form. Otherwise, you have no chances to get a general theorem. Okay? I know that for mathematicians, this kind of reasonings is a little bit difficult. Why? Because they are teaching you only the final result, which is very bad. By the way, I will try to find with you, it is written in my book, but I will find it somewhere. I want to underline this for you. Heuristic reasonings are the essence of mathematics. A mathematician who is not following an heuristic reasoning is half blind. Do you believe that Archimedes was a mathematician? You know, it has been proven that Archimedes has proven rigorously that integral between a and b of x squared dx is equal to b cubed over 3 minus a cubed over 3. He has proven it with Riemann sums. It is written in Greek, but it is written. Okay? He was a big mathematician. And do you know what he did? He wrote a book. This book has the title On the Method. And in this book, he was teaching to his successors, that is us, how he got the idea that this equation is true. So he describes carefully the heuristic method he used for getting the conjecture. After describing this heuristic method, he said, of course, this is not a theorem. Now, I know what I want to prove, and I show you the rigorous demonstration. Okay, I am afraid that modern mathematicians are losing this capacity. So soon, all mathematicians will be in their hyperuranium of abstract concept without no relationship with practice. Engineers will be all practical without any theoretical guidance, and our civilization will have a big collapse. Okay? So we must fight against the cutting the relationship between heuristic reasonings and rigorous theorems. Okay? Good. So let's move another step. We have an equation of this kind. Now we want to prove a theorem. There is a unique solution of this equation verifying initial conditions. So we follow the reasoning of Gursa. Q dot of t. Okay, before doing this, we must do another step. This is a set of n, because q double dot, we have n components. Okay, so we have n equations, scalar equations. So you can write q double dot 1 equal L1 q dot, up to q double dot n equal Ln q dot. Of course, in the first equation, you have all variables here. This is not uncoupled. The acceleration of the first component depends on the value of all other components and of all the velocities of other components. Okay, so this is a true system of n differential equations. Okay, coupled. This is algorithmically and mathematically clumsy, because you have first, second derivatives appearing in the equation.
Will be having n Lagrangians for one system?
No, look, the Lagrangian is 1. Look, okay, let me write this component-wise. This is dl over dq1 minus d over dt of dl over dq dot 1 equals 0. Then you have q2, qn, at the end you have dl over dqn minus d over dt, dl over dq dot n equals 0. Okay? Okay. I'm sorry that this question obliges me to make another example. Okay? So, because you must understand, otherwise it is useless that we run like crazy without understanding. So now we consider q equal q1, q2. We have a system of 2 degrees, with 2 degrees of freedom. And we postulate this L equal. I have 1/2 K1 Q1 minus Q bar 1 square, 1/2 K2, let's call it K11, K22 Q2 minus Q bar 2 square, plus K12 Q2 minus Q bar 2 Q1 minus Q bar 1. This is a quadratic form in the Q1 minus Q bar, Q2 minus Q2. Nothing strange. Okay? Then you have minus 1/2 M1 Q dot 1 minus 1/2 M2 Q dot 2 square. Okay, just for making our friends from Ukraine happy, the potential energy in terms of the differences of Q's and a kinetic energy which is diagonal. Okay? This is a system of coupled oscillators in mechanics. Now we must calculate many derivatives. Okay? So I must calculate dl over dq dot 1. Okay, which is m1 q dot 1. Okay, Then I have dl over dq dot 2, which is m2 q dot 2. Okay, then I have dl over dq1, which is equal to k11 q1 minus q bar 1. Okay, and then I have also k12 q2 minus q bar 2. You agree? Sorry?
Minus M1 Q went up.
Yes, you're right. Thanks, because otherwise we will have troubles. Please check what I'm doing. Okay? And similarly, we will learn that these calculations can be done very quickly using matrices. We will do later. Okay, let us now go slowly. dl over dq2 is equal to k22 q2 minus q bar 2, and then plus k12 q1 minus q bar 1. Okay? Okay, now I must calculate the derivative of this with respect to time and to change its sign. Okay? So please rewrite it. I am writing this on the top because the blackboard allows me to do this. Okay? So rewrite this equation, otherwise you lose the steps. You have this. Okay? Then you must change this sign with minus. Write another passage. Okay? Then you have this plus that equals 0. Okay? So this plus that equals 0. You agree? This is the first Lagrange equation governing my system. Then you have this plus that equals 0. You have the second Lagrange equation. Now, my dear friends, you know how beautiful is Lagrange approach? How many unknowns you have? N. One function for every Lagrangian coordinate. How many equations do you have? Exactly n. It is, I know I'm old, maybe you can say that I'm becoming senile, but I believe me, also when I was young, I became excited by remarking this elegant feature of Lagrange procedure. Other postulations, I will talk about other postulations just for despising them, have the big problem that you must fight all the time for having the same number of equations, that the equations are in the same number as the unknown. Lagrange procedure gives you always the exact number of equations which you need. By the way, if you have f of of x1, x2, xn, and you want to find minima, you calculate the gradient, you impose that the gradient is equal to 0, and you get exactly n equations. All the partial derivatives equal to 0. Minimizing gives you always the same number of equations which you need. Okay? So, now I have answered to your question. One Lagrangian is enough for producing n equations. Okay? So, I wrote formally this system of equations like Q double dot equal L of Q and Q dot. Okay? Now, Hadamard, another French mathematician, discovered that this system of equations is very difficult to handle. By the way, if you have read Arnold, the big book of ordinary differential equations, this part is written very well there. Arnold has been a genius. Probably he died with an ischemic attack when he was on the bicycle. He was in Paris on the bicycle, he had an ischemic attack, he fell down, and since then he has not been himself anymore. He died rather young. Which is the trick which is proposed by Hadamard? Very simple. By the way, Hamilton did something similar, but we will tell this later. So, I introduce two n unknown functions, q and v. Okay? And I write this equation, I write like that. So, first of all, I write v equal q dot. Okay? And then I write v dot equal L of q v dot. V. Okay? It is a trivial substitution which has some nice features I will show you. So, instead of having n equations of second order, I have 2n equations of first order. Okay? And these two systems of equations are equivalent. You agree with this, right? Now, the problem is that the reasonings which we are going to do are much simpler now. I mean, this structure, even if we doubled the number of unknowns, can be solved much simpler than this structure. Okay? So, we prefer to study this problem. So, consider this. Instead of studying this general equation, we have this other general equation. Y prime equal C of y. this is, if you call y this pair, y prime equal a function of y. Okay? So mathematically speaking, you should be able to follow this reasoning. Is it simple for you? I hope, yes, right? I mean, this is the typical thing which engineers don't understand. You have a system of 2n equations, but of first order. Okay? Soon you will understand why we are doing this. Y of t equal y of t0 plus integral between t0 and t of c of y of tau d tau. I hope that you are not surprised by the fact that I changed the name of the integration variable. Please tell me that for you this is simple, otherwise, yeah? Is it simple or not? Yeah? Please. This is Torricelli-Ostrogradsky theorem. Okay? So, to find, look how beautiful it is. It is very easy to impose initial conditions. You replace this with y0, and you have automatically verified the initial conditions. Why? Because the integral between t0 and t0 is 0. Okay? I hope that you will be very upset because I'm telling you these trivial things so that I can ask your pardon, because I was teaching these things to people who found these things difficult. Okay? Let's hope that I will be able to have this course until my retirement so that my life will become happier. Okay? Now, the genius of Gursa. Please, try to follow my reasoning. Okay? Because you should be the right audience for understanding this reasoning. Okay? Here, the unknown is a function. Okay? But before attacking a difficult problem, to find a function, verifying some conditions, we must train ourselves with a simpler problem. Let us write a very simple equation. X squared equal 2. I hope that you are ready to understand what I'm telling you, because you should be all mathematicians. Did you know that Pythagorean school spent many decades working on this problem? Do you know why? There is no fraction which verifies this equation. So if you look for a solution of this equation with x belonging to q, there is no solution. Once more, if I ask myself which is the solution of a given problem, I must tell where I'm looking for the solution. This is essential. Okay. Now, poor Pythagoreans believed that all numbers were rational. So they claimed that x squared equal 2 had no solution. And the big problem is that if you have a triangle with 1 and 1 as a catet, you believe in Pythagoras' theorem. And the hypotenuse is square root of 2. Please, I'm not wasting your time. This course should teach to mathematicians what is a model and how to use it. So, place yourself in the mind of a Pythagorean. I believe that the only numbers are the rational ones. Okay? For me, quantities are fractions. Then I start studying this triangle and I discover that the hypotenuse is not a quantity, has no length. This was a tragedy. The easy solution is to admit that your assumption, Q is the set of all numbers, is wrong. But you know, human beings are very stupid. When they stick to a belief, they don't want to leave it. So there was a big debate about the existence of triangles. Now, we do not know everything because some books have been lost. But Archimedes knew that rational numbers are not all numbers, and he had a definition of real numbers with Dedekind sections. So probably Dedekind did not invent them, he rediscovered them. So there is an ancient definition of Dedekind sections which comes from Greek mathematics. Okay. Now, how do we calculate the solution of this problem? With a sequence of rational numbers approximating the solution. Okay? So, for instance, I do 1 to the square equal 1. 2 to the square equal 4. The power is increasing. So, the solution of this equation is greater than 1 and smaller than 2. Then what I do next? I'm running. I hope you are following. Yes? Usually I must do this in 1 hour. Okay? By the way, what we are doing now, basic ideas in computability theory. I mean, I need to know how to measure the hypotenuse of a triangle. So I need to know how many bricks I need to buy in order to make a perimeter wall in my field which has the shape of a triangle. So this is a practical problem. I need to know the value of square root of 2 with a given approximation, which is the approximation, the length of the brick. So you understand, this is a very serious problem. Very serious. So what I do next? I place 1, 1.1, 1.2, 1.9, 2. I calculate the square of 1.1. Is it smaller or greater than 2? I go ahead, I stop when the power I'm calculating is bigger than 2. So I frame square root of 2 with 1/10 approximation. And I go ahead. The theorem that tells you that x squared equal 2 tells me that I will never find an exact fraction whose square is 2. So this process will continue up to infinity. This is a serious problem from the computation point of view, but if I accept an error of 10 to the minus n, then I can stop after n steps. So what I have? An iterative calculation process which at infinity converges to my exact solution, which is never attained. Are you ready? Can I get an exact solution of this problem? The bad news is that no, not in general. So what can I do? I try with a sequence of approximating functions. And this is the genius idea by Gursa. Okay? Now I will tell you some stories about this. Okay? But let's go. It is clear what I said you? Sure? This is typical of mathematics. You use the solution which you have got from an easier problem to conjecture how to solve a more complicated problem. Okay. So I introduce the sequence y0 of t equal the constant y0. I start with a function of time which is constant. Okay? Then I consider y1 of t equal y0 plus integral between t0 and t of c of y0 d tau. This is a constant, but we don't mind. Okay? Then I give you the recursive rule. Yn plus 1 of t is equal to y0 plus integral between t0 and t of c of yn of tau d tau. So what I'm doing, when I've got the nth step approximation, I build the n plus 1 approximation using the integral form, which is true for the exact solution, with the difference that this has been calculated at the previous step, and yn plus 1 is the subsequent approximation. Okay?
We are doing this because yt is also on both sides of the equation.
Yes.
It's not explicit.
Yes. So what I say is that I got the nth step approximation. I plug in the integral, and in this way I calculate the n plus 1 approximation. Okay?
But what is the philosophy that this is going to work?
The heuristic reason is, okay, this is exactly, you are anticipating my next statement. Let us conjecture, heuristically, that this sequence is converging. Then you calculate the limit on the left and on the right side. So, heuristically, we assume that limit of yn converges to y. Okay, these are functions. So maybe it is better if I write yn of t is equal to y. So let us assume that for some reason we know that this sequence is converging. My dear friends, now there is a big problem. What it means that a sequence of functions is converging? This will open many problems which we will discuss later. But let us do it heuristically for the moment. Okay? So let us assume that in a certain sense this limit exists. Okay? Good. Then I can calculate the limit of the left and the limit of the right side. This limit is y of t. Then the constant as a limit as a constant. Do you have ever studied the theorems of commutation of limit with integral? Okay. Also in this, the Italian school has been very strong. We have Vitali theorem for this. And the theorem of dominated convergence of Lebesgue. Okay? So we have several theorems teaching us how and when the limit and the integral are commuting. Okay? We are doing heuristic reasoning. Okay? So we assume that the limit can go inside. So we have y0 plus integral between t0 and t, limit of Cn of c, y, and tau, d tau. We are discovering that C cannot be a generic one if this process must work. I'm trying to tell you now that C must be continuous. If C is not continuous, there is no chance that this process works. By the way, we will discover that we need more. But this reasoning is suggesting us strongly that if C is not continuous, there are not many chances that this iterative process is converging. Okay?
Because of integration?
No, because I need to commute C with limit. And limit.
Do we need Lipschitz conditions?
Yes.
Because of Lipschitz theorem of...
Yes, you have studied it. We need Lipschitz condition, but I will arrive there.
Oh.
But Lipschitz functions are continuous.
Yes.
So what I'm telling you is that it is useless that you try to find a solution of this problem with C which is not continuous. Okay? So, in order to commute C with the limit, Soviet system collapsed. But look, they studied a lot of good mathematics. I mean, it was a tragedy. When I was in Poland in 1988, I could not find food. But in the corridor of the Polish Academy of Science where I was working, I could find an expert in every field of mathematical physics. It's very strange. Communist system was producing outstanding scientists but no butter. Who knows why? While United States is producing a lot of butter, but not good scientists. Okay, they are importing them from all over the world.
So middle system should be.
Let us try to hope that European Union will be the place where we produce good brains and a lot of butter. Huh? This could be. So, stop about politics. The limit goes inside, and I have a solution of my problem. So, what we have learned out of this heuristic reasoning? First, that the functions C must be at least continuous. Okay? Second, that we need to understand better what it means that a sequence of functions is converging. Okay? Now I tell you a nice story which tells you how dangerous is practice without theory. I have studied Goursat iteration scheme and the theorem of Goursat iteration scheme when I was 19 years old. You know, in Napoli, where I studied, there was a very good Soviet school. We studied all Russian books, Mir Russian books, very cheap. So, when I became professor, I knew that if you write for me an ordinary differential equation in the normal form with C being Lipschitz continuous, I will tell you soon what it means, Lipschitz continuous, then you are safe. There is a unique solution for your ordinary differential equation. So you have a well-posedness problem, a well-posed problem for which well-posedness result is available. So our mechanical determinism, our aspiration towards prediction is verified. Because with your iterative process, you can build a function which is very close to the solution. So you can predict the future. Then, copying Americans, in Italy, they decided to reform the studies for engineering. And this was a tragedy. What they decided? Differential equations, useless for engineers. There is software. They can use the software. So they gave them a software for solving ordinary differential equations as a black box. You type C, and you type initial conditions. It gives you the solution. What is in the black box? Nobody knows. So one day, a PhD student of mine, God should forgive me for having chosen him, he seemed to be clever, but he was an engineer. He came to me and said, "Professor, we must write a paper." I said, "Oh, which paper?" "I have an algorithm which works very well in solving ordinary differential equations. I studied this 3 months. I didn't tell you because I wanted to surprise you." And he explained me, you know, with the attitude of the big genius who is talking with an old senile person who may not understand what he's telling him. "This algorithm When I said, look, this is called Coursa iteration, and it was conceived in 18th century, beginning 19th century, he treated me as somebody who wanted to sabotage his career. Since then, he did not speak to me anymore, because I had dared to question his genius. This is very dangerous. We must know what has been already done if we want to progress. Otherwise, we waste our time rediscovering periodically what has been already discovered. First. Second, do you believe that my PhD student was more clever than Coursa? By the way, he said that Lipschitz condition is useless, because, his code was working without his thinking about Lipschitz condition. Now, let us make another step. Peano wrote, for having fun, this equation: y prime equal square root of y. Okay, before we proceed, in this audience you are all mathematicians, so for you, square root of y cubed, logarithm of y are all functions, so you say, why not? The first reaction of an engineer is, I don't mind about square root of y. Why you want to study this equation? Okay. Pathologic equations are very important for understanding when a process works. So it is very good for conjecturing the right properties to be assumed to prove theorems. Now, what is doing square root of y? This is the plot. The tangent in 0 is infinite. Remember, when you have something going to infinity, a danger. I don't know if Cantor or Poincaré said that the devil is causing some functions to become infinity to cause us troubles. Okay? Now, square root of y is a continuous function. So this example, this is a famous equation, is Peano differential equation. Now, this is not a course in mathematical analysis, so I will not try to teach you the solution of Peano problem, but I tell you the result. There are many solutions for the initial problem, for this equation. So there is no uniqueness. However, Peano proved existence result. So, an ordinary differential equation of the form y dot equal c of y with c continuous has a solution, but it is not in general unique. Okay? Why I'm telling you this? You must frame your conjectures with examples and counter-examples. With the previous reasoning, we said, okay, C has to be at least continuous. Otherwise, I cannot exchange the limit. So, the first conjecture is, What if I suppose C to be continuous? Can I find a unique solution? Piano answer. Sorry, my dear friend. C continuous is enough for existence, it is not enough for uniqueness. So, if you are Epicurean, I tell you exactly what it means to be Epicurean. Epicurean means you believe that science can allow you the exact predictions of the evolution of physical systems. So, mechanical determinism is a big part of Epicurean philosophy. Did you ever heard the name of Democritus, the inventor of the theory of atoms? He was an Epicurean. By the way, in Soviet schools, they were teaching philosophy of science. And still there are students I'm professor in Russia for 2 more years, and I met very clever students knowing deeply the philosophy of science, which is very important because in philosophy of science they teach exactly this kind of things, this kind of reasonings. So, continuous is required, continuity is required, but it is not enough to get uniqueness. Now, we need an assumption for getting rid of this kind of pathologic behavior. Lipschitz, look, I don't remember exactly the spelling, but look in web, in Wikipedia, for instance, you look for existence and uniqueness of differential equations, you find the spelling. I will give you some lectures note. Lipschitz conditions is the following. So the increment of C is bounded. K is called Lipschitz constant. Is bounded by the increment of the independent variable. Actually, this condition is so-called uniform Lipschitz continuity because K is the same for every pairs y1, y2. Okay? This condition is very useful for proving the existence and uniqueness theorem. So, if we have 8 minutes, I think. We have 2 hours today, right?
Yes.
So, if C is continuous, you have existence. If C is Lipschitz, obviously C is continuous. Okay? But you have also uniqueness. Do we know something for conditions which are intermediate? Not really. I'm not aware of any intermediate result. So I don't know if Lipschitz is really necessary and every weakened assumption leads to non-uniqueness. Okay? Okay. Now, let us try to understand. Okay, I have 8 minutes, so I tell you what we will try to do in the next lectures. What it means that two functions are close? We need a topology in the set of functions. Do you know what is a topology? Do you know, yes or no?
No.
No. Do you know what is a metric space?
Yes.
Everybody knows what is a metric space. Okay. Topological spaces are more general than metric spaces. Okay. So let us, we are lucky. A matrix is enough for talking about Gauss theorem. So, I will recall you what is a metric space. You have a set of objects and you have a function d defined in S, Cartesian S, having values in R+, which is called matrix or distance. Which are the properties of this? The distance between S1 and S2 is equal to the distance between S2 and S1. Okay? The distance between S1 and S2 equals 0 implies S1 is equal to S2. The first is symmetry condition. The second is, I don't know if it has a name. Then you have triangular condition. ds1, S2, let us call S3. The distance between S1 and S2 and S3 is smaller or equal the distance S1 to S2 plus the distance S2 to S3. In this audience, this definition should not surprise anybody. But I want to tell you some nice comments. One could believe that there is a unique distance for everything. It's not true. I give you an example, then we stop the lecture, we'll continue this later. You know, Napoli is a very chaotic city. If you have 2 points in Napoli, you can measure the distance between 2 points, these 2 points, in several ways. You can use the matrix, the Euclidean matrix, the number of kilometers from one place to the other. Or you can use the time needed for going from one place to the other. Or you can use walking, or by car, or by public means of transportation. You get different estimates of the distance. There are 2 points in Napoli whose distance is 2 kilometers, and walking you need 25 minutes. By car you need 1 hour. Okay? So, there are different concepts of distance, and we must learn how to abstract, how to make abstract the concept of distance for incorporating all these meanings. And then we apply to our problem of ordinary differential equations. Okay? Okay, so we will meet tomorrow.